Hello everyone, today I want to go ahead and cover hybridization in super easy terms. I know this topic may come off as scary to some of you, but I just want to go ahead and share some tips and tricks and patterns that I've discovered when I was taking this class, and I want to go ahead and share it with you guys in hopes of making OChem a little bit easier. So yeah, let's get started. But before we do, I do want to just go and put a disclaimer out there. There may be some cases where this pattern may not work. So in that case, please do have, a good understanding of orbitals and energy configurations and things of that sort. But in today's video, I'm going to go ahead and help you, solve hybridization questions using this pattern. So before we go ahead and touch on some sample problems, let's go ahead and review this table. So when we are looking at an sp hybridized atom, we are looking at a linear geometry. A linear geometry corresponds to a 180-degree bond angle. When we are looking at an sp2 hybridized atom, we are looking at a trigonal planar. A trigonal planar geometry has a 120-degree bond angle. And then with sp3, we are looking at a tetrahedral geometry with a bond angle of 109.5 degrees. So this topic was... I do not know what happened there, sorry. But this topic was covered in Gen Chem 1 or 2, I'm not sure, but it was covered in Gen Chem. Thankfully in OChem you don't really need, or in OChem 1, you do not need to know the geometry or as extensive of a geometry as you did for Gen Chem 1 and 2. You just need to know these three basics for hybridization, which hopefully makes learning a lot more easier on your part. So just have this table in mind, have it memorized so that, it can be helpful to you when you're answering questions. So let's go ahead and look at some example problems. So before we start on this problem, I want to go ahead and give some, basic understanding of hybridization. So when we are talking about hybridization, what we're really looking at is how many groups is bonded to that atom that we are trying to determine the hybridization of. So in this case, this carbon is bonded to 4 different groups. Because it's bonded to 4 different groups, this is going to be an sp3 hybridized atom. The way you know this is by adding up the exponents. So there's an imaginary one there, right? And then you can add these 2 exponents to give you 4, which is the exact number of groups that is bonded to this carbon. Let's do another one. So for example, there's a carbon double bonded to a carbon, and single bonded to 2 other carbons. So in this case, we have 1, 2, and 3. 3 groups. That would correspond to an sp2 hybridization because when we add the exponents together, it gives us 3, which is 3 groups. So that's correct. So that is one way you can determine hybridization in simple terms. Additionally, you need to know that lone pairs matter, okay? So lone pairs matter. So for example, when we are trying to determine the hybridization of nitrogen, to a hydrogen and 2 carbons with a lone pair, right? Well, we know that this is 1 group, 2 group, 3 group. This lone pair is also a group. You don't just ignore it or exclude it. You count it as a group. So that would be 1, 2, 3, 4. That is 4 groups. So that would be an sp3 hybridized nitrogen. So now that we've covered that, let's kind of look at a special example. And I say special because there is actually a rule that you need to follow. An atom that has a lone pair, if it is bonded to an sp2 hybridized carbon, then this atom, no matter what its original hybridization was, will also become sp2 hybridized. Now, I know that was a bunch of words, so let's kind of see in person. It's a lot more easier than it sounds, trust me. So, yeah. So let's look, and we are determining, oh, that's too light. We are determining the hybridization of nitrogen. So when you look at an example, just automatically fill in anything that's missing. So can you think of something that's missing in this? If you said lone pairs, or if you thought lone pairs, that is correct. So this nitrogen is actually bonded to that carbon. It's bonded to this carbon. It's bonded to a hydrogen. But it also has two lone pairs that is not really drawn, because in organic chemistry, we like to do everything easier. So if we don't need to draw it, we won't draw it. But you kind of need to know that it's still there. Just because it's not drawn doesn't mean it's just gone, right? So in this case, this nitrogen is bonded to that first group, this second group, this third group, and this fourth group. So you might say that this is an sp3 hybridized nitrogen, right? Well, using this rule, we are going to look at what the nitrogen is bonded to. So it is bonded to this hydrogen right here. It's bonded to this carbon right here, and it's bonded to this carbon right here. When we look at this carbon, let's figure out the hybridization of this. So that's 1, 2, and 3 groups that this carbon is bonded to. That makes that an sp2 hybridized carbon. Because this nitrogen is bonded to an sp2 carbon, this nitrogen will also become sp2 hybridized. Okay? So again, if this atom with a lone pair is bonded to an sp2 carbon, it will also become an sp2 atom. Okay? Let's look at a more extensive example of this. So we have 4 molecules or 4 atoms that we are trying to find the hybridization of. So let's go ahead and draw in any missing lone pairs. So we know this oxygen has 2 lone pairs. We know this nitrogen has 1 lone pair, and that's it. So it is asking us for the hybridization of this oxygen, labeled O1. So we know that this has 1, 2, 3. But does this oxygen have lone pairs? Yes, it does. So we need to consider this rule, right? If it's bonded to an sp2 carbon. Yes, it is. This carbon has 1, 2, 3, so it is an sp2 hybridized carbon. Therefore, this oxygen is also an sp2 carbon. But this oxygen was already originally an sp2 carbon, because again, this is 1, 2, 3 groups that it's bonded to. So you don't really need to worry about what it's bonded to, because this is already sp2, right? So sp2, so this is not a special case, because oxygen, or O1, was already originally sp2 hybridized. There's no change in hybridization. Let's look at C2. So this is the carbon we were talking about. We said that it's bonded to 1 group here, 2 group here, and the 3rd group here, which makes that an sp2 hybridized carbon. Let's look at this nitrogen. This nitrogen has, again, 1, 2, 3, 4. But this nitrogen has a lone pair. So we're going to go ahead and see if it's bonded to any sp2 hybridized carbons, which again, it is. Now, because this was originally an sp3 nitrogen, because it's bonded to an sp2 carbon, it will also become an sp2 atom. This means it's undergoing a change in hybridization, which makes this a special case. So what I like to do is just put a star around that, because it is going to come in use later. So again, the hybridization of N3 would be sp2. let's look at C4 right here. We have this first group, this second group, this third group. And remember, in organic chemistry, they do not really draw out the hydrogens, but you need to have a mutual understanding that it's there, okay? Let me just go and erase this. But yeah, you need to know it's there. So don't forget that hydrogen. So we have 1, 2. I'm sorry, okay. So we have that 1 there, this 2, 3, and then this 4, which makes this carbon sp3. Again, you don't need to worry about it being, connected or bonded to this sp2 carbon because there is no lone pairs, right? So C4 is going to be sp3. Now, the only special case that we've had was N3, right? So O1 did not undergo any change in hybridization. It stayed sp2. So the orbital of the lone pair would be sp2 because it's not a special case. What about N3? Well, N3 is a special case. So whenever we have special cases, the pattern that I've picked up, again, may not work for every single problem, but the ones that I did encounter really worked well with this pattern. So again, a special cases, the orbital of lone pair will always be in P. Okay. Don't know what happened there, but the orbital of the lone pair will always be in P, and the bond angle of that lone pair will always be 90 degrees for special cases. This is that secret pattern that I wanted to share with you guys. Again, may not always work, but it has worked well with many problems. So again, use that as you will. So again, N3, the orbital of lone pair, because N3 is a special case, the orbital would be P, okay? And then we're looking at the ideal bond angle of O1. O1 was not a special case. Therefore, we're going to go back to that table. O1 was sp2, so it's going to have a 120 degree ideal bond angle. So, again, this is 120 degrees. N3, because it was that special case, this is what the ideal bond angle would be. It would be 90 degrees. So that is how you solve any hybridization problems. This pattern, if it's a special case, which means it changed from one hybridization to another because of a certain scenario, you always want to look at P. That would be the orbital of the lone pair, and it would be 90 degrees. And again, that is if there is a special case. So I hope that, makes sense to you guys. If you do have any questions, please do let me know. I'll try my best to answer them. And, have a great time studying. I hope this video made some sense to you, if not too much. But yeah, I'll see you next time. Bye.